In the previous session, we looked at linear equations and specifically uh, linear equations, m linear equations in m unknowns. So m was equal to n. So here we are going to look at solution of m linear equations in n unknowns. So which means here m is not equal to n. Here m is the equations, number of equations, and n is the number of unknowns. Now, when m is not equal to n, there exists a solution if and only if the coefficient matrix A and the augmented matrix C have the same rank. So, if rank of A is less than rank of C, then AX equal to B is inconsistent. If the rank is same, then there is a solution. If rank of A is less than rank of C, then it is inconsistent. If rank of A is equal to rank of C is equal to R, let's say we represent this as R, which is equal to the number of unknowns, then n minus R equal to, since R is equal to n, so n minus n, which is equal to 0, which means none of the variables are free, and hence there exists a unique solution. If rank of A is equal to rank of C equal to R, and here R is not equal to n, then we end up with n minus R free variables, and the others are in terms of each other and free variables, and we evaluate the solution, the set of solution, by assigning values to the free variables. If rank of A is equal to rank of C is less than n, then we have infinite number of solutions. Okay, let's look at some theorems. Right, so theorem: if rank of A is less than rank of C, the system of equations AX equal to B are inconsistent. So let's prove this by contradiction. Let AX equal to B be consistent, and let rank of C equal to R, which is greater than rank of A, or we could have said rank of A is less than rank of C, which implies that there exists at least one non-zero determinant, let's say delta R, of order R in the matrix C, that is the augmented matrix, which implies that the delta R must contain the last column of C, because remember, otherwise it is in A, but we are given that rank of C is greater than rank of A. Since rank of C is greater than rank of A, okay, assuming delta R lies in the top right corner of C, since rank of A is less than R, first R rows of A are linearly dependent. Therefore, R linear functions f1, f2, fr forming first R rows of A are linearly dependent, which implies that there exists K1, K2, and so on up to Kr, not all 0, such that K1 F1 plus K2 F2 and so on up to Kr Fr is equal to 0. Yes. So remember, F1, F2 are linear functions forming the first R rows of A. So if we map it to the augmented matrix, we would end up with F1 minus B1 plus K2 F2 minus B2 and so on to Kr Fr minus Br is equal to 0. Let's simplify this. K1 F1 minus K1 B1 plus K2 F2 minus K2 B2 and so on Kr Fr minus Kr Br is equal to 0. Now let's take the negative terms to the other side. So K1 F1 plus K2 F2 Kr Br is equal to K1 B1 plus K2 B2 and so on up to Kr Br. Now remember, K1, K2, Kr are constants, scalar. Similarly, B1, B2, Br are constants. So this entire thing we can replace it with a single K. So which implies K1 F1 plus K2 F2 Kr Br is equal to K. Now K is not equal to 0, because otherwise what will happen? F1, F2, Fr would be linearly dependent, which is not possible, because remember, the top right hand corner determinant of order R in C is not 0. Delta R is not equal to 0. Yes. Okay. But the first R equations are F1 equal to F2 equal to F3, Fr is equal to 0, which implies that K is equal to 0. So here we arrived at K not equal to 0. Here we are saying K equal to 0. So therefore a contradiction. So if rank of A is less than rank of C, then the system of equations are inconsistent. Okay, that is one first theorem. Let's look at the next theorem. Now, the theorem says if rank of A is equal to rank of C, here A is the coefficient matrix, C is the augmented matrix, the equations or system of equations Ax equal to B are consistent. Okay, let's see. Remember, A is a submatrix of the augmented matrix C. So rank of A is going to be less than or equal to rank of C. Okay, let's reduce the augmented matrix C to row reduced echelon form by elementary operations. Okay, so let's say R is equal to 1 0 0 beta 1, 0 1 0 beta 2, 0 0 0 beta 3, 0 0 0 beta m. Okay, instead of zeros here on the top triangle, there might be some values, but that's not the point. We are reducing it to the row echelon form. If at least one of the beta r plus 1 to be beta m is not zero. See, wherever you have all zeros, but beta, the corresponding beta is not zero, then the number of non-zero rows in the coefficient matrix A is not equal to the number of non-zero rows in the augmented matrix. Yes. So therefore, rank of A is less than rank of C, and which implies that at least one of the equations, remember here, all the row elements is 0. But if the corresponding beta is not 0, that means what? That equation is going to be improper. So at least one of the equations, beta j is equal to 0, where j goes from r plus 1 to m, is false. As I said, all are 0, but if beta is not 0, that means that statement is false. So therefore, Ax equal to B is inconsistent. Now, if all beta r plus 1 equal to beta r plus 2 and so on up to beta m is equal to 0, that means wherever all the elements are 0 and the corresponding beta is also 0, that means what? Rank of A is equal to rank of C, which implies that Ax equal to B has one or more solutions. Yes. So here, first point is, if rank of A is equal to rank of C is equal to R is equal to N, then you end up with a unique solution. The second one is, if a rank of A is equal to rank of C is equal to R, which is less than N, then you have infinite solutions. Okay, I think that's enough for today. Bye.